Hello everyone, back to our course on MN22062 drone technology. And I am your faculty, Ranjit, and we'll start with unit number 3 from, from here. So it's a pleasure to meet you today, and we'll dwell into what I believe one of the most exciting and rapid evolvement field in modern engineering. Over the next few weeks or days, we'll be exploring the incredible world of unmanned aerial system from their basic principle to complex application that are reshaping industries around the globe. This course is designed to provide you with a comprehensive understanding of mechanism, electronics, and software that make these amazing missions possible. As a mechanical engineer, the principle of aerodynamics, structural design, material science, and control theory are the fundamental to our discipline, and drone technology serves as a perfect practical application where all these areas are covered. Today, we are diving into particular part of the subject, which is unit number 3, which focus on advanced drone operation and control system. This unit marks a significant step from the fundamental we have previously discussed. We have moved beyond simple manual flight and basic drone construction to explore the very intelligence that allows drone to perform complex tasks autonomously. When we talk about advanced operation, we are referring to capacities like precision navigation in cluttery environment, coordinated swarm robo, long endurance surveillance mission, and the ability for drone to make decisions in real time without direct human intervention. These are the operation that unlocks the true potential of this technology, moving it from a hobbyist gadget to an indispensable tool for agriculture, logistic, search, research, rescue, and national defense. The key to enable these advanced operations lies in the second part of our unit, which is titled as control system. A drone's control system isn't the brain and the central nervous system. It is the intricate network of sensors, processors, and algorithms that interprets data from the environment and translates it into precise physical action, adjusting the motor speed, rotational propellers, and stabilizing the aircraft against external forces like wind. In this unit, we will study on these systems. We will examine the hardware like accelerometer, gyroscope, and the GPS module. And most importantly, we'll be focusing on software and control logic that forms the core of the drone's autonomy. We'll study the mathematical model that describes the drone's flight dynamics and learn how feedback loop like the famous PID controller are implemented to achieve stable and reliable flight. Our goal is to equip you not just with the knowledge of how these systems work, but with the foundational skill to design, simulate, and even implement control strategies of your own. This control is crucial because it prepares you for the cutting edge of research and development in this field, paving the way for innovation in autonomous navigation and intelligent guidance system. So let's start on our journey into the advanced world of drone operation and control. Now that we have set the stage for our unit on advanced drone operation and control system, let's dive into the specifics of what we'll be covering. These slides provide an introduction and a roadmap for our discussion. First, it's important that we are all on the same page regarding terminology. We'll be focusing heavily on what are known as the Small Unmanned Aircraft or SUAS and a subset of those often called as MAVs, which stands as the Micro Air Vehicle. The distinct between these and the large drone or the traditional aircraft is arbitrary. It is defined by specific set of characteristics. As the slide notes, these definitions are based on factors like wingspan, power mode of operation, and very critical payload capacities. For example, a small wingspan presents unique aerodynamic challenges and opportunities, allowing these aircraft to operate in a confined space where large systems cannot go. Their power system, typically electric batteries, dictate their endurance and flight performance, creating a constant engineering trade-off between flight time and the energy required for onboard system, and their payload capacity are perhaps the most defining constraint, driving innovation in sensor miniaturization and effective system design. The reason we focus on intensely on these smaller systems is due to their rapid expanding role in both military and civilian sector. The growing role of unmanned aircraft system or UAS is transforming how we approach a variety of tasks. In defense application, these small drones have become indispensable for reconnaissance and surveillance. Their ability to provide real-time intelligence from the air without risking human life is a monumental advantage. They can be deployed quickly to gather information, monitor situation, and enhance the situational awareness of ground force. However, the most explosive growth we have seen is in the civil and commercial arenas, as depicted in the image on this slide. The precision agriculture is a prime example. Here, the drone equipped with specialized sensor can monitor crop health, identify areas needing water or nutrients, and even apply treatment with incredible accuracy. This leads to higher yield, lower cost, and more suitable approaches to farming. Beyond the field, these systems are crucial for environmental monitoring. They are used to track wildlife, survey remote ecosystem, and assess the impact of climate change in the way that were previously impracticable or uh, prohibited by expenses. With this context in mind, we can turn to the core purpose of this unit. Our primary objective here is to prepare you for research in the key area that enables all these advanced application, autonomous navigation, guidance, and control system for NAVS. This is where we move from being user of the technology to become its creator. We'll explore how a drone perceives its environment using sensor, how it plans a path to destination while avoiding obstacle. That's navigation. And we'll study the guidance algorithm that can keep the drone on the path, correcting for wind and other disturbances. And finally, we will dwell deep into the control system that translate guidance command into precise motor and actuator response needed for stable flight. By the end of this unit, you should have the foundational knowledge to not only understand these complex systems, but to begin contribution to research and development that will define the future of autonomous flight. While the potential for micro air vehicle is immense, their widespread adaptation isn't without significant obstacle. This slide outlines the key challenges and the future direction that engineers, policymakers, and the business in the field are currently navigating. These challenges can be broadly categorized into technical, economical, and regulatory hurdles, and understanding them helps frame the importance of work we are doing in this course. First, let's look at the technical challenges. This industry is in the constant push for increased reliability, extended capacities, and improved ease of use. Increased reliability is absolutely critical. For drone to be trusted with valuable payload or to operate in close proximity to people and infrastructure, they must be exceptionally dispensable. This means designing systems that are resilient to component failure, software glitches, and environmental factors like high wind or signal loss. Alongside the reliability is the demand for extended capacity. User wants drone that can fly longer, carry more sophisticated sensor, and operate with great autonomy in complex environment. This drive research into more efficient battery technology, lighter and stronger material, and more advanced artificial intelligence for navigation and decision making. Finally, for this technology to become truly uh, unique, we need improved access, ease of use. A drone shouldn't require a team of highly specialized engineers to operate. The goal is to create a system that are intuitive and can be deployed quickly and easily by professionals in various fields. Whether it is a farmer checking crop or a first responder survey a disaster area. Next, we face significant economic challenges. The core issue is the need for reducing cost while maintaining high standards for performance and safety. This is a classic engineering balancing act. The high-end sensor, processor, and the communication system that provides the best performance and the reliability are often the most expensive. As we push for mass adaptation, the price point has to come down to make the technology accessible to more industries and small businesses. However, this cost reduction cannot be at the expensive rate. We cannot compromise the quality of the component or software in the way that would endangered people or properties. Therefore, the challenge lies in the innovation, finding new manufacturing techniques, developing more efficient algorithms that can run on a less expensive hardware, and designing a system in a way that is inherently cost effective without sacrificing the quality. Perhaps the most complex barrier is the set of regulatory hurdles we face. The primary issue here is the integration of unmanned aircraft into national and international airspace. Our skies are already a crowded and meticulously managed system for manned aviation. The safely introduced the, sta- the safe, safety introduces millions of autonomous drones into the environment is an enormously undertaking task. The government and aviation authorities around the world are working to develop a new rules and new air traffic management system specifically for unmanned aircraft that are they are grappling with questions of certification, pilot licensing, operational restriction, and piracy concerns. Creating a comprehensive legal and regulatory framework that ensures safety without stifling innovation is one of the most critical steps needed for the drone industry to reach its full potential. Given these broader challenges, our focus area in this unit becomes clear. We will be concentrating on the technical core of the problem, the guiding and controlling of limited payload small and miniature aircraft system. By advancing our understanding of these fundamental principles, we are directly contributing to the solution for the challenges we have just discussed. Better guidance and control algorithm lead to more reliable and capable drone. More efficient control system can reduce computational requirement, which in turn can lower cost and proven track record for safety reliability control in foundation upon which our future regulation will be built. This is the heart of engineering work that will unlock the future of MAVS. To begin solving the challenges we just discussed, we need a robust and a well thought out design. This slide presents an integrated view of typical MAV system architecture. Think of this as the blueprint of an autonomous drone, showing us how the different parts work together to create an intelligent flying machine. We'll break down this architecture into its core component. First, we have the fundamental system component. This starts with the most obvious part, the unmanned aircraft itself, which is the physical airframe. This includes the body, wings or arms, motors, propellers, and everything that makes up the physical structure. This is the hardware that actually moves through the air. The brain of this hardware is the autopilot, which is the onboard computer that executes the flight software. To understand this environment and its own status, the drone relies on a suite of sensors. These are the drone's eye, ear, and which includes inertial measurement unit (IMU) with accelerometer and gyroscope, a GPS for location, a barometer for altitude, and a magnetometer for heading. However, the raw data from these sensors can be noisy or inaccurate. That's where the state emission comes in, state estimation comes in. This is a critical software module that takes all the incoming sensor data and fuse it together to produce a single accurate and reliable estimate of the drone's current state, its precision, position, orientation, and velocity. Building upon these core components are the navigational component, which handles the higher level logic of autonomous flight. The process begins with path planner, giving given a mission such as surveying this area or fly from point A to point B. The path planner's job is to compute a safe and an efficient route. It acts like a GPS in a car, planning the entire journey before you start. Once a path is generated, the path manager takes over. Its role in the following is to follow the path in issuing immediate tactical command like fly forward at the speed or turn to this heading. It is the component that ensures MAV stay on the route defined by the planner. Finally, these high-level commands are sent to the control system. These are low-level system that translates commands like pitch up into exact adjustment in motor speed required to make that happen, ensuring aircraft remain stable and responsive throughout the maneuver. The power of this design lies in its modular architecture. As the slide notes, each blocks interact with other, and this interaction is what enables complex autonomous behavior. The sensor provides data to state estimator, which provides the drone's current state to the path manager, which executes the plan from the path planner by sending command to the control system, which then drives the physical aircraft. It is continuous feedback loop. This modularity makes the system easier to develop, debug, and upgrade as an engineer can work on individual blocks without having to redesign the entire system. Ultimately, this brings us to the core of our unit, which the hardware is essential. Our focus will be on the design for the software algorithm that enables autonomous and self and semi-autonomous flight. This is the sophistication of the software, the state estimators, the planners, and the controller that truly defines the capacity of modern MAV. Having laid out the architecture of MAV, the next logical question is how we actually design the intelligent software that runs on it. The answer lies in our design philosophy, which is centered on the principle of modeling for control. We cannot control what we cannot describe. Therefore, our first step is always to create a mathematical representation of the drone and its environment. Our process begins by translating the physical system into a simulation. To do this, we need to create a detailed mathematical model that captures every important aspects of drone behavior. This includes modeling of its rigid body kinematics, which describes the geometry of its motion, its position, look velocity and orientation without considering the forces involved. Next, modeling its dynamics, which is where we apply physics to understand how forces and dark causes the drone to accelerate and rotate. We must develop a model for aerodynamics, which accounts for the complex force of lift and drag generated as the drones moves through the air. Finally, we need to model the sensor themselves, capturing their characteristics, limitation, and potential for noise. The ultimate goal is to build a comprehensive simulation that acts as a digital twin, a virtual drone that behaves almost exactly like its real-world counterpart. This allows us to test our ideas safely and cost-effectively in a virtual environment. While highly detailed model is perfect for simulation, it can be too complex for designing the control algorithm themselves. This leads us to the next step, creating simplified design models for control. We develop different models for different tasks. For low-level control, such as autopilot function that keeps the plot stable, we often use simplified model that accurately captures the drone's behavior during specific maneuvers like hovering. These models might ignore certain complex aerodynamic effects to make the mathematics of designing a stable feedback control more manageable. For high-level guidance system like Park Planner we discussed early, we can use a simpler model. For example, we might model the drone as a single point in space, ignoring its orientation entirely. Because for long-range path planning, only its position and velocity are relevant. The key is to strategically simplify reality to create a model that is just complex enough for the task at hand, but more, but no more. This entire approach is embedded within a iterative design process. It's a cycle that continuously refine our design until it meets the requirement performance and reliability standard. The process starts with the design phase, where we create our own guidance and control algorithm using our simplified mathematical tool. Next, we move to simulation, where we test these algorithms extensively on our high fidelity digital twin to see how they perform under wide range of conditions. Once we are confined in the simulation result, we proceed to test on actual hardware mishaps in controlled lab environment at first. Finally, the first step is the fully implementation on the physical system for real-world test drives. The data from these real-world tests is invaluable if often revealed shortcoming in our model, which we then use to go back to the design phase and improve them. This continuous loop of design, simulation, testing, and implementation is fundamental to developing the robust and sophisticated autonomous system of the future. As we delve deeper into the mathematical model of MAV, we must first establish a clear and concise way to describe their motion, position, and orientation. This is accomplished by using a set of coordinate frames which are the subject of this slide. The importance of coordinate system cannot be overstated. They are absolutely essential for driving and understanding MAV dynamic behavior. Without a rigorous framework for defining where the drone is and how it is oriented, we simply cannot write the equation that governs its flight. Think it of this way: a drone's GPS might report its location in terms of latitude and longitude and Earth fixed frame, while its inertial accelerometer measures force received to the drone's own body. To make sense of both pieces of information, we need a mathematical way to relate these different points of view. To manage this complexity, we use several key coordinate frames. As the slide list, these include inertia, vehicle 1, vehicle, vehicle 2, body stability, and wind, wind frames. Let's briefly touch on what some of these represents. The inertial frame or the earth frame is our fixed reference. You can think of it as being attached to the ground with axis pointing north, east, and down. This is the frame in which Newton's law of motion applied directly. The body frame is another critical one. It is fixed to the MAV itself, with the axis typically pointing out the front, the right wing, and the down through the bottom of the aircraft. The round sensor, like its gyroscope, make measurement in its frame, and the forces from the propellers are applied in the frame. The other frames, like the wind frame, are crucial for aerodynamics as they are aligned with the airflow over the vehicle, which is essential for calculating lift and drag. Each frame is chosen to simplify the description of particular physical force or measurement. Having multiple coordinate frame is only useful if we can translate information between them. This process is handled through mathematical transformation. Specifically, rotating matrices are used to convert coordinate between frames. The rotational matrix is a powerful tool that allows us to take vector description in one frame, say the force of the gravity in the inertial frame, and, and calculating its component in another frame, like the drone's body frame. This tells the autopilot how the force of gravity is affecting the drone's pitch and roll at specific. These transformations are fundamentally operational and that performs continuously by software running on the drone's flight controller, which represents here by the Arduino pilot board. The input, such as the data from the GPS module, are processed through these coordinate transformation to inform the control algorithm, which then generates the output to the motor. This constant conversation of information between the frame at the very heart of how MAE navigates its world. Now that we have established the need for coordinate frame, we need to practically way to describe the drone's orientation within those frames. This brings us to the most common method for representation an aircraft altitude, Euler's angle. This is a mathematical language we use to define how drone is tilting or pointing in space. Euler's angle consists of a set of three rotational roll, pitch, and yaw. Let's define these intuitively. The roll angle represents by pi, describing the rotation around the MAVs longitudinal axis, the line running from its nose to its tail. This is the motion would be seen as the wings back left or right. The pitch angle theta is the rotation around lateral axis which runs from the tip to tip, wingtip to wingtip. This corresponds to the nose of the aircraft tilting up or down. Finally, yaw angle phi, psi uh, is the rotation around vertical axis causing the nose to turn left or right like a car steering. Together, these three roll, pitch, and yaw angle describe aircraft attitude relative to immediate field. Essentially, any possible rotation of the drone can be described by some combination of these three numbers. It is very important to note that the order in which you apply these three rotation matters. If you roll the drone first and then pitch it, and you will end up in a different orientation than if you had pitched it first and then rolled it. To ensure consistency, engineers and scientists agree on a specific convention. The common use rotational sequence for aircraft is chi, theta, and phi sequence, which means that to define the final orientation, we start the aircraft level and pointing north. That then we apply the yaw rotation following the pitch rotation, and finally the roll rotation. This standardized sequence is crucial for ensuring that the control software correctly interprets the drone altitude, while Euler's angle are intuitive and uh, widely used. They have one significant drawback known as the gimbal lock. The gimbal lock is a mathematical singularity that occurs when a drone reaches a pitch angle or of plus or minus degree means its position straightens up or straightens down. At this precise orientation, the angle, the axis of roll and yaw becomes aligned, and as a result, they become indistinguishable from each other. This creates a mathematical problem where the drones effectively loses a degree of rotational freedom. The flight controller can no longer uniquely determine the aircraft's orientation, which can lead to instability and a complete loss of control. Well, this is not an issue for many standard flight operation. It is a critical consideration in high performance aerobic maneuver. This limitation is primary reason why more advanced systems sometimes uses a more complex mathematical representation like quadrature to avoid the problem of gimbal lock entirely. So far, we have discussed how to represent the MAV's orientation or altitude using Euler's angle. Now, we need to broaden our perspective to describe MAV's total motion through space. This is the domination of kinematics, which is the formal study of motion without considering the force and torque that causes it. The slides break down the full set of variable or state that we need to trace to have a complete picture of drone's movement at any given moment. For rigid body like MAV motion in three-dimensional space, there are total of 12 states that we must define. First, we need to know where the drone is in space. These are translation position states. We define the position using three coordinates. North represents as Pn, east represents as Pe, and down represents as Pd. These coordinates are all measured relative to inertial fluid. This means we have a fixed starting point on the ground, and we measure ground's position as distance along these three axes from the origin. The northeast down or NED conversation is standard in aerospace and gives us an unambiguous global position for aircraft next. We need to describe how fast the aircraft is moving. These are its inertial velocities. Interestingly, we don't typically measure this in the fixed inertial frame. Instead, we use body frame components UVW. This velocity projected onto body axis. The variable u represents the forward force, v is the speed to the right, and w is the speed downwards, all from the drone's perspective. This is more intuitive for control because the thrust from the propeller and the aerodynamic force are also guaranteed along these body axes. The next set of state should be familiar from our previous discussion. They define the drone's angular position. This is simply the drone's orientation in space, which we describe using Euler's angle, phi, g, and theta. As we cover these three angle representation roll, pitch, and yaw of the aircraft, and together they give us a complete picture of its altitude. Finally, we just as we have linear velocity to describe how fast the drone is moving, we have angular velocity to describe how fast it is rotating. They are known as body rates, P, Q, R. These three variables describe the rotational motion of the MAVs. Specifically, P is the pitch rate or the how fast the drone is rotating around its forward axis. Q is the pitch rate or how quickly its nose is moving up or down. And R is the yaw rate, which is how fast it is turning left or right. These values are typically measured directly by the gyroscope on the onboard of the drone. Together, these tell state 3 for position and 3 for linear velocity, 3 for angular position, and 3 for angular velocity. Gives us a complete kinematic description of the MAVs. The entire job of the flight controller is to understand and manage these 12 variations to achieve stable and controlled flight. Now that we have the language of kinematics to describe how MAVs move, we can advance to the next critical topic, dynamics. While kinematic answer how, uh, dynamics answers why. This is the study of the force and movement that cause the motion we observe. This is where we apply the fundamental laws of physics to create a model that can predict the MAV's behavior. In cornerstone of the dynamics is the Newton's second law. As the slide states, this law is applied to translation. F equal to mass into acceleration and rotation equal to m equal to j into omega, the degree of freedom. For translating motion, this is a similar concept that sums all the external forces acting on the drone is equal to its mass multiplied by its acceleration. These forces include gravity, the thrust from the propeller, and the aerodynamic forces like lift and drag. By summing these forces, we can determine how the drone will accelerate and move through space. Similarly, for rotational motion, the sum of all equal moments or torque is equal to the drone's inertial matrix multiplied by its angular acceleration. These moments, such as those generated by the different thrust of the propellers, are what causes the drone to roll, pitch, and yaw. The critical detail in applying these law is the choice of reference frame. The Newton's law hold in internal frame. An inertial reference is one that is not acceleration. For our purpose, the fixed northeast drone frame we attach to the Earth's surface is considered an inertial frame. This means that all of our primary calculation for dynamic must have their motion reference to the fixed frame. This introduces a significant challenge because many of our forces and measurements occur in the drone's own body frame, which is constantly rotating to correct uh, to correctly apply in Newton's law. We must use the coordinate transformation we discussed earlier to translate everything back to the inertial frame, a process that adds mathematical complexity but is essential for accuracy. Focusing on the rotational dynamics, we encounter a key property of the airframe known as the inertia matrix, represented by J. In linear motion, mass is the single value that measures an object's position to acceleration. In rotation, the situation is more complex. The inertial matrix J is a concept that measures position to angular acceleration about body's axis. It is a matrix or a grid of numbers because an object's resistance to bring spun depend on its shape and how its mass is distributed relative to the axis of rotation. For example, a drone with a wide, flat body will be having hard to pitch or roll than is to yaw. The inertia matrix captures all of its geometrical information. This fundamental property of the drone's physical design is crucial for accurately modeling and controlling its rotational motion. The diagram you see on the slide illustrates the very focus and the moment acting on a single rotor that we must sum up and use in dynamic equation. After establishing the general framework of the rigid body dynamics, we can now begin to populate our equation of motion with the specific force and moment that act on the MAV. This slide focuses on the two most fundamental forces, gravity, which is constantly pulling the drone downward, and the force from the propulsion system, which counteracts gravity and allows for controlled flight. First, we'll consider gravitational force. This is the simplest force to model, but it is always represented, it always presents, and control system must constantly work to overcome it. The gravitational force, which can be denoted by F to the base g, and is the propulsion to mass and gravitational constant. This is simply the weight of the aircraft. A heavier drone requires more thrust to hover. This force also predicts in its direction as it is always acting in the downward direction relating to fixed inertial frame. While it is a simple vector, its component in the drone's body frame will change as the drone roll and pitch, and the flight controller must continuously account for it to maintain stability. Next, we have the force generated by the propulsion system, which for the multi-rotor MAV means the propellers. The primary force is the propeller's thrust, Fp. This is the lift force that generated by pressure difference created by the spinning airfoils of the propeller blades. For the purpose of control system design, this thrust is modeled as a function of throttling delta T and airspeed VA. The throttling system setting delta T is the command sent from the autopilot to the electronic speed controller, determining how fast the motor spins. The higher throttle results in more thrust. However, the air speed VA also plays a role. The efficiency of a propeller and the amount of thrust it produces can change depending on how fast the drone is already moving through the air. The sophisticated model will account for its effect. Of course, generating thrust isn't the only simple effect a spinning propeller has. According to Newton's third law, for every action that is an equal and opposite reaction. This leads to the creation of propeller torque MP. In order to spin a propeller, the motor must apply a torque to it. In reaction, the propellers apply an equal and opposite torque to the MAV ball. This reaction torque is what causes the body of the drone to want to spin. On quadcopter, this is cleverly managed by spinning two propellers clockwise and two counterclockwise, so its reaction torque cancels each other out during normal flight. Control other yaw is achieved by deliberately balancing these torque. It is important to note that this torque is proportional to the square of the propeller's angular velocity. This means that you you speed up a motor, the reaction torque increases as much as fast than the thrust does. This nonlinear relationship is the key characteristic that the flight control software must be designed to handle precisely. In addition to the force of gravity and the propulsion, we must also consider the force that are generated by MEVs interacting with the air itself. These are the aerodynamic force, and this slide focuses on two primary components, lift and drag. The origin of all aerodynamic force is the same. MAV movement, MAV's movement through air creates pressure distribution around the surfaces. As the aircraft's body, wing and the propeller pushes their way through the air, they create variation in air pressure around them. The sum of these pressure differences result in a net force on the aircraft, which we can then break down into more useful components. The first component is lift, denoted by F lift. F lift is defined as the force perpendicular to the airflow. It is commonly misconception that lift always acts upwards, while it does counteracts weight in level 5. It is truly defined is based on the direction of the incoming air. For modeling purpose, this force is considered to act at a single point of the aircraft known as aerodynamic center. The second component is the drag or the F drag. F drag or the drag is the force parallel to the airflow and it is acting in the direction that is opposite to the motion. As shown in the diagram, the drag is a resistive force that the Drawn's thrust must overcome to accelerate and maintain its forward speed. These forces are not constant. They change dramatically depends on how the MAV is flying. To predict these forces under different conditions, we use what we know as the aerodynamic coefficient. These are non-dimensional coefficients. For lift, drag, and pitch moment, we have CL, CB, and CL, respectively. These captures the dynamic characteristics of aircraft shape. The great advantage of using these coefficients is that they remain consistently regardless of the aircraft size, speed, or the altitude at which it flies. The value of these coefficients are primarily influenced by the angle of attack, the angular rate, and the control surface. The angle of attack, which is the angle between the aircraft and the oncoming airflow, is the most significant factor in determining lift. The angular rate, how fast the MAV is pitching, rolling, or yawing, also alters the airflow and creates a damping force that can crucially be stabilized. Finally, on aircraft with control surface like the ailerons or the elevator deflects these surfaces intentionally, changes the aerodynamic coefficient to generate the moment needed to control the aircraft's altitude. By understanding how these factors influence the coefficient, we can create a comprehensive model that accurately predicts the aerodynamic forces on MAV in any phase of the flight. Just as the aerodynamic forces causes MAV to move, these also causes it to rotate. These rotational effects are called aerodynamic moment and they are the key to control the aircraft's altitude. The slide explores these movements and the mechanism we use to manipulate them for controlled flight. We can divide the MAV's rotational behavior into two categories. The first, longitudinal dynamics, aerodynamics. This category deals with the moment causing motion in the pitch plane. The pitch plane is a vertical plane that cuts through the aircraft from nose to tail. The primarily pitching moment M is the task that causes the nose to pitch up or down. Managing this moment is fundamental to control the aircraft's speed and altitude. The second category is the lateral aerodynamics. This covers motion, all other motion, including the moment causing motion along the JB axis, which relates to side slip, and the crucial rotational motion is in the role capital I and Ya, N, which is denoted by the letter M. The rolling moment I causes the aircraft to back and the yawing moment N causes its nose to swing from side to side. For many NAVs, especially fixed wing design, These controlling movements are generated by physical control surfaces. These are hinged flaps on wings and tail that the autopilot can move. The primary control surfaces are elevators, pitch control, and ailerons, roll control, and the rudder, yaw control. The fundamental principle at, at work is that the surface deflecting effect. When the control surface is deflected, it changes the shape of the aerofoil, which in turn leads to change in aerodynamic forces and moment. For example, deflecting the elevator up creates an downward force on the tail, causing a pitch movement that raises the nose of the aircraft. By precisely moving these surfaces, the autopilot can generate the exact movement needed to guide the aircraft. However, for multi-rotor MAVs, like the one shown in the diagram, control is achieved without these surfaces. Instead, the multi-rotor generates movement by precisely varying the thrust of their individual motor. As the diagram illustrates, the drone is subjected to a force of gravity. F, uh, F gravity is equal to mass gravity acting at its center. To make the drone roll as indicated by the angle theta roll, the control system would increase the thrust from the motor on one side and decrease the thrust on the opposite side. This creates a net torque or moment uh, that the rolls the aircraft. The same principle applied for generating pitch and yaw moments. So whether it's through a subtle deflection of control surface or a rapid adjustment of motor speed, the core principle is same. We create controlled movement to change the MAV's altitude and direct its flight.